Hi. Today we're going to discuss the Bohr model for the one electron atom. And Bohr developed this theory when at that time the atom was thought to obey the planetary model. So here's the planetary model. There's the nucleus, and the electron is in an orbit around it. And the kind of equations that scientists knew at that time, they knew that written as proportionality relations, they knew that EK was the kinetic energy and is proportional to velocity squared. They knew the virial theorem for electrons. EK is proportional to ET, which is proportional to EP for electrons in atoms. They knew the potential energy of an electron in an atom is proportional to the charge of the nucleus divided by R. And they also knew proportionality relations about momentum. Momentum is mv. Momentum is proportional to velocity, since the mass of the electron is constant. And they knew the de Broglie relation, P equals h over lambda, so P is proportional to 1 over lambda. And Bohr recognized that with these kinds of equations, electrons have wavelengths. While they may be in orbits, there are waves in orbits. And so thinking about that, he realized the waves would have to look something like this. So in these pictures here, we see that there are 5 wavelengths, 5 lambdas going in a circle. So the number of waves, which we're going to call n, times the wavelength is equal to 2 pi r, the circumference of the circle. And the same thing is true on the picture on the right. There are 6 waves, 6 wavelengths, 6 lambdas. 6 times lambda is 2 pi r. And written as a proportionality relationship, he saw that n times lambda is proportional to r, and he gave n a name. He gave it the name the principal quantum number. Okay, well, we don't need this picture anymore, so I'm going to move it up top again, and now we'll use these equations. And first, let's get that proportionality relationship over here. N lambda is proportional to R. Okay, so these are our 6 proportionality relations. Let's give them names, letters. This is A. This one will be B, C, D, E. And because Bohr recognized that the orbits are waves, he recognized the new proportionality relationship, F. And so let's put these together. EK is proportional to V squared by A, and V is proportional to momentum by D. So EK is going to be proportional to V squared, and V squared will be proportional to P squared. P, if we look at relation E, is proportional to 1 over lambda, so P squared is proportional to 1 over lambda squared. That's by E. Let's now look at relationship B. EK is proportional to EP. So there's EK over here, and it's proportional to EP. That's by relationship B. And EP by relationship C is proportional to Z over R. And now he could use his new relationship F. R is proportional to N over lambda. And now we've used all 6 relationships, and we can start doing some algebra. We'll use the 1 over lambda squared is proportional to z over n over lambda. So 1 over lambda squared is proportional to z over n over lambda. We can cancel a lambda on both sides. 1 over lambda is proportional to z over n. We can now flip it. Lambda is proportional to n over z. And we know from proportionality relationship F that R is proportional to n lambda. That's relationship F. And we now know that lambda is n over z, and therefore we get that R is proportional to n squared over z. And finally, we have ET is proportional to EP. That's the virial relationship B. And EP is proportional to Z over R. That's relationship C. And we know that R over here is proportional to n squared over Z. So if we plug that in, Z over R becomes Z squared over n squared. And now we're going to take these relations and write them as equalities. R is proportional to n squared over z. That means R is going to be equal to a proportionality constant, which we're going to call A0, n squared over z. And this A0 is the Bohr radius. ET is proportional to z squared over n. ET will be equal to a proportionality constant, which is minus RH, z squared over n squared, where RH is the Rydberg constant. And these two equations, the one for the total energy and the one for the size of the radius, are the equations of the Bohr model. And we're going to practice this derivation tomorrow.